Let's get started. Any questions, comments, issues before we get going? Anybody? No, no, no. All right. Well, oh, too many noises. Hopefully you can't hear those. Um, so we finished talking about depth of field, and was your second assignment due, I believe, today. So any questions about that? Anybody? No. Okay. So today I want to talk. Well, today we want to do two things. Talk about our um, last technical topic, I guess, and then work on images in Lightroom. So talk about the develop module in Lightroom. But first, our topic of the day. Sorry, just looking for something here. Uh, is something called color temperature and white balance. So have any of you fiddled around with either of these things to your knowledge? Anybody? Color temperature, the white balance settings on your camera? No,
No,
no, okay.
no.
Uh, somebody, and I can't remember whose assignment it was, but somebody's assignment was shot in part in the wrong, what's called white balance. So maybe we'll take a look at those in a bit. Um, Color temperature is a way that we use to describe colors. So in general parlance, as they say, we talk about colors as colors: red, orange, yellow, and so on. Um, but those colors actually represent or are wavelengths of light that we can see. So I want to talk about that. That's one thing I want to talk about today. So let me just bring some of this stuff up on Canvas. This thing is so slow. Okay, so can you see the desktop showing a page that says color temperature? Okay. Um, what we see are wavelengths of color, wavelengths um, that are a small, minuscule portion of the entire amount of light that is put out by the sun. And so that entire spectrum is called the electromagnetic spectrum, or the spectrum of light. And stars, such as our sun, put out light. And some stars put out light more in some areas than in others. So I want to talk about that for a little bit. So Roy G. Biv, ROYGBIV, stands for these colors: red, orange, yellow, green, blue, indigo, and violet. And these are the colors that we can see. And so they make up what's called the visible portion of the spectrum of light. They are, however, only a very small portion of the entire amount of light that is put out by our sun and by stars. So these colors, again, are wavelengths. And the longer wavelengths are red and beyond red into the areas we can't see. And as we go across towards violet and beyond, the wavelengths get shorter and shorter. Beyond what we can see in the longer wavelengths are TV and radio waves. So we've encountered, at least theoretically, all of these waves. Microwaves, which we use for cooking. Infrared. Have any of you heard of infrared light? If you have, tell me what you've heard. Anybody? No? Nobody? Um, I'm sure you've seen some movies, maybe action movies or police type movies, where somebody has a long rifle with a scope on it, a spotting scope that allows them to see like through buildings, and they can see people moving, and those people are represented by heat registers. So the inside is really bluish, white blue, and then it goes out to red and yellow or something like that. Um, so what those sites are doing are picking up infrared radiation from from those people. And that actually is real. Those scopes do exist. Those types of guns do exist. So they're seeing something that we can't actually see because the cells that make up our eyes that allow us to see color um, can't see into that register. There are some films also that are sensitive to the infrared portion of the spectrum and can record into that area that we cannot see. Um, then just beyond infrared are the colors that we can see: red, orange, yellow, green, blue, indigo, and violet. And then beyond violet, in the shorter portion, the shorter wave portion of the spectrum, is ultraviolet. And I'm sure we've all heard of ultraviolet radiation and how damaging it is to our skin and eyes and to plants and so on. So these cosmic rays, so to speak, are generally blocked by our environment, the air, and so on. Um, uh, there was great talk of a hole in the ozone layer created by fluorocarbons and other nasty, things that we have produced. And when we don't have that protection of ozone and so on, then these rays, such as ultraviolet, can affect us more intensely. So ultraviolet, then X-rays. We've heard of X-rays for diagnostic purposes, medical purposes, also for the use in treatments of some diseases such as cancer. Even beyond X-rays are gamma rays, which are put out by certain particles, certain radioactive isotopes. So these are all things that we cannot see. Obviously, in photography, generally, and in life, we deal with the portion of the spectrum that we can see. And we don't describe the colors as their specific wavelengths in nanometers or whatever they are, but as colors. But scientifically and also photographically, colors are also described by something called their color temperature. And that is a way of measuring the colors. And so the color temperature, or the temperature scale that is used, is not Fahrenheit or centigrade, which we use to measure physical temperatures, but the Kelvin scale. And so the Kelvin scale was devised by Lord Kelvin, who measured what's called black body radiation. So essentially, he heated up some coal and measured the different colors that were put out at different temperatures, and then quantified them into this scale. And the scale is not, it doesn't stand completely on its own. It has a relationship to the centigrade scale. So, for example, 0 degrees Kelvin which is called absolute zero, is a theoretical point. So those of you who have taken chemistry and especially physics may have heard of 0 degrees Kelvin, and that's a theoretical point. No one is sure that it can actually be reached. It is supposedly the point where all molecular motion ceases. It's so cold, I guess, that the motion of electrons around the nucleus of atoms completely ceases. That temperature in centigrade is minus 273, I think, degrees centigrade. So there is a relationship between those two scales. We don't deal with that, however. We deal with much, much higher color temperatures. And so I've written out some of the biggies here. So you have a sense of the scale. When we think about colors, we have actually a kind of emotional response. But even in a descriptive way, we think of colors in the reverse of the Kelvin scale. So if you look at this scale here, you can see that the higher temperatures, 11,000, 10,000 Kelvin, are blue. And as the color temperature decreases, it goes down into the red area. So reds have very low color temperatures relative to the blue colors. When we think of colors, we think of reds as being warm. So if we see an image, a painting or a photograph that has a lot of reds or golds in it, we describe it as warm or having warmth. Images that have a lot of blues, greens, purples, we describe as cool or cold. And that is the reverse of the Kelvin scale. So in the Kelvin scale, the higher the color temperature, the more blue the light, and the lower the color temperature, the more red. So I've given you some of the kind of anchors within the scale. So the highest color temperatures that we tend to deal with on a regular basis are in the 11 to 10,000 degree Kelvin range, and that is very, very blue light. So in deep shade, where there's absolutely no direct sun, just before sunrise and just after sunset. So if you happen to be awake at, 6 in the morning or 7 in the morning, the light is very, very blue. It's bluish purple. And as the sun starts to rise, it gets lighter and lighter, but it stays a bluish purple until the sun comes above the horizon. And immediately it comes above the horizon, the light changes drastically. It goes from that bluish purple to a golden red. And so the color temperature actually drops by about 7,000 degrees immediately. And when the sun is setting, as the sun sets, as it gets lower in the sky, it gets more and more golden and then orangey red. And then immediately it dips below the horizon, the light completely changes, and it's bluish purple. It no longer has really any red or gold in it. So those times, just before sunrise, just after sunset, have a very high color temperature. The next color temperature that I've listed here is 8,000 Kelvin, or 8,000 degrees Kelvin. And that also is a very blue light, but not quite as blue. And you get that in shade. So in the shade of a building, for example, when you have very heavy cloud cover, not like today in Santa Cruz, it's cloudy. It's foggy, but the fog is high. It's not stormy weather. Um, 8,000 degrees Kelvin would be stormy weather where the cloud cover comes down lower, and the light is actually pretty bluish, though we don't necessarily perceive it as such. So when we experience the world, our brains compensate for changes in types of light. So this red piece of tissue paper looks red if we're in the shade, if it's cloudy out, if it's sunny out, when we're inside under different types of light, incandescent light, fluorescent light. We still perceive this as a red piece of paper. But photographically, cameras and films can't compensate very well for those changes in the types of light. And so we see color casts in photographs. And I'll talk about that further in a little bit. Okay, so that's 8,000 Kelvin. 7,000 Kelvin is a cloudy day. So today, again, in Santa Cruz, it's foggy, but it's pretty high cloud cover. It's bright. And so there's still a bluish color cast, but not as much. So that's at about 7,000 Kelvin. 5,500 Kelvin is daylight. So that's a biggie. And that's depending on the time of year and where you are on the planet, from about 10 a.m. to 2 p.m. roughly, could be 9 to 3 in the summer. Daylight, and so outside on a bright sunny day. And that is the color temperature that our cameras and our color films are designed to shoot for and to look natural in. Electronic flashes, so the flashes that are built into our cameras, are also balanced to daylight. And so wherever the flash happens to hit, if you're using it, those areas should look as if it was shot under daylight. After daylight, we have what's called tungsten light. And tungsten light has more red or orange or gold in it. So again, as the color temperature decreases, the light shifts from blue to red. And so tungsten lights have a somewhat more reddish or golden hue,